All right, let's take a look at this one. I want to first remind you that when you have the graph of e to the x, it looks like this, right? And so when you have this graph of e to the x, we know that the limit as x goes to negative infinity of that is what? Well, when x goes to minus infinity, these y values are getting smaller and smaller. So the limit is 0, right? So this limit here, and also, if I take the graph of x squared, it looks like this, right? Notice on this, when x goes to minus infinity of x squared, it's basically I'm taking a large negative number and then I'm squaring it so I get a large positive number. So here the limit is infinity. And you can see that from the graph too. When x goes to minus infinity, the y values are getting larger and larger positive. So what is the form of this limit? Well, like we just said, this x squared goes to plus infinity. This e to the x here goes to 0. So our form this time is infinity times 0, right? And this is also an indeterminate form. And that means we should probably try to use L'Hopital's rule. But L'Hopital's rule only really applies to the form infinity over infinity or 0 over 0. Or negative infinity over infinity, etc. So that's not of the correct form. So we need to kind of change this a little bit to make it into the form where we can use L'Hopital's rule on. Why don't we just get rid of this here, now that we have recalled that. The trick here is like this. We want to write this as a fraction, because L'Hopital's rule kind of needs a fraction, right? So we could go like this. Why don't we just bring this e to the x to the bottom? So we'll write x squared over e to the minus x. Now, what is... Oh, sorry, the limit is supposed to be going to minus infinity. Now, what is the form of this limit? Well, when x goes to minus infinity, like we said, x squared goes to infinity. So the top is going to positive infinity. What about the bottom? Well, just a second ago I sketched the graph of e to the x, right? E to the minus x is basically the graph of that, except it's been reflected about the y-axis. So this time it grows up to plus infinity on the left-hand side. So we see this time that if we do the limit as x goes to minus infinity of e to the minus x, this is going to be plus infinity, right? It's not really surprising, because if x is a large negative number, and then I do minus x, I get a large positive number. And e raised to a large positive number is a very large positive number. So this bottom, all I'm trying to say here is this bottom also goes to infinity. I'll just erase this here. So we have a form that L'Hopital's rule applies to, right? So let's do it. Let's apply L'Hopital's rule to this. The derivative of the top is 2x. The derivative of the bottom is minus e to the minus x, right? By the chain rule. Or maybe you'd prefer me to go a little bit slower. I don't know. I can write the derivative of e to the x, or e to the minus x, is e to the minus x. And then by the chain rule, we multiply by the derivative of negative x, which is negative 1. So we get, like I said, negative... Let me just get rid of those brackets, because we don't need them. Okay, so this is fine. But what's the form of this now? Do we have a nice form, or again, do we have an indeterminate form? Well, when x goes to minus infinity, 2 times x goes to minus infinity as well, right? 2 times a large negative number is a large negative number. Like we said before, when x goes to minus infinity, this here goes to plus infinity. But that minus in front makes it minus infinity. And this is also an acceptable form. This is an indeterminate form, definitely. And L'Hopital's rule can be applied for this as well. So let's do it. Take the derivative of the top and bottom separately. The derivative of the top is 2. What is the derivative of the bottom? Well, minus comes out front, e to the minus x, and then by chain rule times the derivative of negative x, which is negative 1. So there we go. Why don't I just move this here? Excuse me. Let's go like that. Just get some more room. So let's just clean up this bottom here. So it's 2 over negative 1 times negative 1 is just plus 1. So those negative 1s just disappear, and we get that. Now look, the top doesn't go to infinity anymore. Why don't we bring the e to the minus x back up to the top like we did, like it was at the beginning? Becomes e to the positive x now. And now we're in really good shape. This limit is just fine here. When x goes to minus infinity, like we said, well, actually we didn't say that, but it's obvious. Remember the graph of e to the x, like we said, is this. So when x goes to minus infinity, e to the x goes to 0. And 2 times 0 is 0. So this limit is 2 times 0, which is 0. So that's our answer for this one. I hope that makes sense. We had to apply L'Hopital's rule twice there. And notice, to get any progress here, we had to move this e to the minus x to the bottom, okay? I just want to say something, like, let's say we would have moved the x squared to the bottom instead. Would that have worked or not? This is just a separate little discussion here. What if we would have tried this? Limit as x goes to minus infinity, and we would have kept the e to the x on top like it was, but we would have moved the x squared to the bottom. Then it would become this, right? Would this have worked? Well, you know, this form here, this is... what is this form here? This is 0 over 0, isn't it? And that is an acceptable form for L'Hopital's rule. Do you see that it's 0 over 0? When x is a large negative number, e to the x is a small positive number. So the top goes to 0. We can see that right here. And 1 over x squared, or x to the minus 2, that also goes to 0, right? Remember the graph of that? It looks like this. This is the graph of 1 over x squared, or x to the minus 2, whatever you prefer. And when x goes to minus infinity, that also goes to 0. So this has the form 0 over 0. So I can use L'Hopital's rule. Let's see what happens. The derivative of the top is just e to the x. The derivative of the bottom is minus 2x to the minus 3. Now this is not really that great, because this power went from minus 2 to minus 3. And that doesn't really help. We could use L'Hopital's rule again, but then this would be minus 4 power, and it gets actually more complicated as you keep using L'Hopital's rule. Whereas notice here we had x squared and then x, and then it was gone. And that's why L'Hopital's rule worked here, but it would not work here. So whenever you have this indeterminate form of infinity times 0, and you use the strategy of moving one of the factors to the bottom, it actually does matter which factor you choose. So in this one, moving the e to the x to the bottom works just fine. We get the answer of 0. But if we would have tried to move x squared to the bottom, we would just keep going on and never really get anywhere. So don't do it like this. This is the way we want to do this question, okay? So the answer for this one is 0.